Hello everyone! In this lesson we shall speak about physical quantities characterizing the magnetic properties of matter, and also we shall classify the materials for their magnetic properties. Any atom in the solid may carry a local magnetic moment μn, where n is the number of a given atom, and n goes from 1 to the capital N, where the latter is the number of atoms in the sample. The total magnetic moment is the vector sum of μn, as n goes from 1 to capital N, and depends on n. It is convenient to consider a specific magnetic moment called magnetization. In general, magnetization can also result from electric currents flowing inside the sample. As a rule, but not necessarily, magnetization arises upon application of an external magnetic field of strength h, and is linear in h at small h. Here, chi alpha beta is the tensor of magnetic susceptibility. In isotropic substance, magnetization is simply the product of chi and h for any direction in space. In the case that M is not linear in h, the differential magnetic susceptibility is used. Magnetic induction B, or magnetic field in the sample, is the sum of external and induced fields. Here, μ is the magnetic permeability, not to be confused with the magnetic moment. Magnetic permeability determines what happens with the external magnetic field inside the substance. Magnetic field in substance can be enhanced, reduced, or remain unchanged. All these formulae are written in CGS system of units, so the magnetic constant μ0, commonly called the vacuum permeability, did not appear here. All materials, not only solids, may be categorized according to their magnetization M in an external magnetic field H. Materials can be magnetic and non-magnetic. The atoms of non-magnetic materials do not have magnetic moments, therefore their magnetization is equal to 0, and magnetic induction is equal to external magnetic field. Note that in antiferromagnets, magnetization is equal to 0 as well, while the differential magnetic susceptibility is non-zero. We shall see this below. There are many examples of non-magnetic materials. Among them are wood, rubber, leather, and other natural materials. Diamagnetic materials create an induced magnetic field in a direction opposite to an externally applied magnetic field, and are repelled by the applied magnetic field. In other words, magnetic field in the sample is weakened. When exposed to a field, a negative magnetization is produced, and thus the susceptibility is negative. Note that when the external field is 0, the magnetization is 0 as well. Another characteristic behavior of diamagnetic materials is that the magnetic susceptibility is temperature independent. Some well-known diamagnetic materials are water, nitrogen, salt, and so on. Superconductors are called the ideal or perfect diamagnetic materials. In superconductors, magnetic field is fully expelled from the sample due to the Meissner effect. Let us see the illustration of the Meissner effect. Magnetic field lines, represented as blue arrows, are excluded from a superconductor when it is below its critical temperature. So, the characteristic of superconductivity appears when the temperature T is lowered below a critical temperature. Well-known superconducting substances are lead, mercury, zinc, and so on. Paramagnetic materials can form internal induced magnetic field in the direction of the applied external magnetic field. Like diamagnetism, the magnetization is 0 when the field is removed, but in the presence of a field there is a partial alignment of the atomic magnetic moments in the direction of the field, resulting in a net positive magnetization and positive susceptibility. At normal temperatures and in moderate magnetic fields, the paramagnetic susceptibility is small, but larger than the diamagnetic contribution. Many iron-bearing minerals are paramagnetic at room temperature, among them biotite, siderite, pyrite, and so on. Note that in real materials, one area can be diamagnetic and the other area can be paramagnetic. Therefore, the total magnetic susceptibility depends on the specific features of the system. Ferromagnetic materials exhibit parallel alignment of magnetic moments, resulting in large net magnetization, even in the absence of a magnetic field. The elements iron, cobalt and nickel and their alloys are typical ferromagnetic materials. In the case of ferromagnetism, the magnetic susceptibility is meaningless, while the differential magnetic susceptibility makes sense. Ferromagnetism is observed only below the material-dependent Curie temperature, or the temperature of ferromagnetic phase transition. Curie temperature can be sufficiently large. For example, for iron, it is about 1000 Kelvin. The magnetic structure of antiferromagnets and ferrimagnets is composed of two magnetic sublattices. In ferrimagnets, the magnetic moments of these sublattices are not equal and result in a net magnetic moment. Ferrimagnetism is therefore similar to ferromagnetism. However, ferro and ferrimagnets have very different magnetic ordering. The examples of ferrimagnets are magnetite, double fluorides, some sulfides, and selenides. If the magnetic moments of different sublattices are exactly equal but opposite, the net moment is zero. This type of magnetic ordering is called antiferromagnetism. Antiferromagnetism is observed only below the material-dependent Néel temperature, or the temperature of antiferromagnetic phase transition. Well-known examples of antiferromagnetic materials are chromium, manganese, and rare earth metals. In this lesson, we have introduced the physical quantities characterizing the magnetic properties of matter. They are magnetization, magnetic susceptibility, magnetic induction, and magnetic permeability. We have learned that materials can be magnetic and non-magnetic. Magnetic materials are divided into 5 broad categories: diamagnetic materials, paramagnetic materials, ferromagnetic materials, antiferromagnetic materials, and ferrimagnetic materials. Also, we have noted that superconductors are perfect or ideal diamagnets.